about bases, where in level 63 was all about acids. Okay, so the Arrhenius concept defined a base as a substance that produces hydroxide ions in aqueous solution, and the Bronsted-Lowry told us that acids are a proton acceptor, meaning they get that H+1. So bases like sodium hydroxide and potassium hydroxide fit both of these descriptions because they both contain hydroxides, and they completely dissociate when dissolved in aqueous solution. So we classify sodium hydroxide and potassium hydroxide as strong bases in the same sense that they completely dissociate, just like strong acids do, which we learned that back in level 62. All hydroxides that contain group 1A and group 2A metals are strong bases. But it's important to note that a group 2A metal has a +2 charge. So that means when you balance out the charges, you are actually going to contain 2 moles of hydroxide for every 1 mole of metal, or 1 mole of the overall compound. Okay, alkaline earth metal hydroxides are not very soluble, but they can have advantages, usually medical advantages. Tums contains calcium hydroxide, and milk of magnesia is the picture on the right, and that contains magnesium hydroxide, and those are both good for when you have an upset stomach. So let's calculate the pH of sodium hydroxide, just like we did when we had the strong acids back in 63. So to calculate the pH, we need to know something to plug into our equations that we used in 63. Well, in our solution, we are containing, when this completely dissolves, we have sodium ions, we have hydroxide ions, and don't forget, water is still in there because it is a solution. Okay, well, since this is a basic solution, we're concerned mostly with the hydroxide, and since it's completely broken up, all of the hydroxide ions are coming from the sodium hydroxide, nothing to do with the water. Okay, so that means that the molarity of this compound solution is equal to the molarity of the OH. So the concentration of the OH is equal to 5.0 times 10 to the negative 2 molar. So now we need pH, and there's multiple ways to solve for this, but I like to use the pH and pOH equations. So the pOH is equal to the negative log of the OH concentration, which is 5.0 times 10 to the negative second. If you want to type that in without scientific notation, you can, because that's just 0.05. And the pOH is equal to 1.30. Remember, sig figs in the hydroxide is equal to the decimal places in the pOH. Well, we want pH, not pOH, so then to get the pH, we subtract from 14. So the pH is 12.70. So this is a good indicator for us to tell us that yes, in fact, it is a basic solution because the pH is greater than 7, so it's basic. The closer you get to 14, the more basic it is. So this is a very strong basic solution. We can't have proton acceptors without the OH, right? So many types of proton acceptors don't actually have the OHs, but they can increase the concentration of hydroxide ion by the reaction because they're going to be dissolved in water. So this, for example, is ammonia with water. So if you want to label, the NH3 is ammonia, ammonia, and plus the water, and that makes the ammonium ion and a hydroxide. So what actually happens in when I have to order ammonia for chemistry, we don't just label it in the chemical world as ammonia because we know that this dissociation reaction is happening. So instead, sometimes it's just labeled as ammonium hydroxide because it is technically an ionic compound solution because we know that this will be present in the solution. So we can create a hydroxide even if it doesn't have an OH within the compound when it is dissolved in water. Other non-hydroxide proton acceptors are all listed here, and you do have pictures of them in your note packet. So the general reaction between a base and water, especially when you don't have hydroxide included, is B stands for base plus water, yields the base with a proton added to it and hydroxide. So at equilibrium, the Kb, which stands for the base's equilibrium constant, is the conjugate acid times the hydroxide over the original base concentration. You don't include water because it is a liquid. Weak bases can be represented with these Kb's because they don't dissociate as well, just like weak acids don't dissociate as well. So here's a list of some Kb's for you in case you need them, but usually they'll be given to you. So we will, when solving out if you had to find the Kb or if you have to find the pH or something like we did at the end of level 64 with weak acids, we can do the same with weak bases. So we want the pH for a 15 molar solution of ammonia, and I give you the Kb. Okay, so the dissociation reaction for when ammonia reacts with water will be the NH3 reacts with water, and so we are going to take one hydrogen from the water this time and add it to the ammonia to get our ammonium. So the NH4 plus 1 because we had an H and a positive charge. And then what's left over from the water is our hydroxide. Okay, well, so then we need to know that, yes, water is a part of that, but because the Kb has a -5, we can go ahead and just assume that all of the hydroxide is being produced mainly by the dissociation of the ammonia. Okay, so we're going to use the ammonia instead. So our Kb expression is going to be the NH4 times BOH over the NH3. Okay, remember water is a liquid, so we don't include it. Now we have to do our ice chart to figure out what to plug in here, right? So the concentration, the 15, goes with the original ammonia. That's our I line. And we're not including water because water is a liquid. And we don't have any of our ions on the product side yet. So our change, we're losing from what we have and we're gaining to our zeros. So at equilibrium, we would have 15.0 minus x and then x and x. Remember, we are going to be able to do assumptions this chapter, so we're going to assume that x will be so small that we don't need to include it in our denominator. So we'll have 1.8 times 10 to the -5 for Kb equals, and we have two x's, so I'm going to square my x over 15 because I'm dropping it for the assumption. So then when you solve for x is equal to 0.016. And that is actually, since we have x right there, is the concentration of the hydroxide ion. Okay, so then now we can use that to help us solve for the pH. So I'm going to go ahead, what I like to do, I do the POH first, so I'm going to take the negative log of my 0.016. So my POH is 1.78. So then subtract from 14 to get my pH. And my pH is 12.32, which again tells us that yes, this is a basic solution because it is greater than 7. It's actually very strong because it's greater than 9. All right, that's it for level 64. So our problems today are number 30, 92, 95, and 98A.